Hi, in this video, we're going to take a look at random forest. Random forest is by far overwhelmingly my favorite model for supervised learning. I have had tons of consistent success using random forest. And every single time I've been on a project and I didn't use random forest for supervised learning, my random forest model was competing pretty well with the model I actually put into production. So I love this model structure. I use this a lot. I lean on this. One thing that's really, really nice about this is that because it's a tree-based model, I don't have to do a lot of data prep. And so I have used this during meetings in real time. Somebody asks a question, they're interested in something. I know where the data is. I grab that data, I drop it in random forest, and pretty quickly I can start giving answers, which is a huge advantage compared to other model structures where I have to go through and do a whole bunch of data prep, data cleaning, things like that. Random forest tends to handle raw data very, very well. Now, I've seen pretty consistently, over the years that random forest doesn't come out as the top model, but it's usually pretty close to the top. And in my spreadsheet SQL table work, my work has focused on what you would call spreadsheet problems, where your data can be represented very cleanly with a spreadsheet, and very consistently, random forest has been like one that will deliver. If it's not the best, it's close to the best. All right, so how does random forest work? All right, well, what we're going to do is we're going to make a forest of decision trees, but you've got the word random in there, right? All right, the random part is that when I go to build an individual tree, I'm going to randomly select a subset of predictor variables, and I'm going to randomly select a subset of the observations. And that's where the random aspect of random forest. So every single tree, or practically speaking, every single tree in my forest of decision trees use a different collection of predictor variables and a different collection of training data. Now, when we do the selection on the observations to include, sometimes we'll use just a subset. Sometimes we can use bootstrapping. It depends on which version, which you're using. If I'm using R, if I'm using SAS, if I'm using Python, there's going to be nuances and differences between each of them. So I'm going to talk about just one version here, and hopefully the concept will get you ready if you're working on a different one. And so we're going to take an ensemble of all these different trees. Every single tree had a different collection of predictor variables considered. Every single tree had a different collection of training data considered. Now, when they do the selection, I've got my training data. It's going to randomly select within that training data. So the overall training data for every single tree stays the same, but the random sample of those observations will change. All right, now what's going to end up happening is I'm going to have a whole bunch of decision trees. And somehow I have to take maybe 500 decision trees, put them all together into one model. How are we going to do that? Well, if I'm doing a classification, what I'm going to do is I'm going to just vote. We'll vote to see which ones are, which level is for each time I take an observation, I'm going to make a prediction on. I'm going to have 500 trees that predict the class, and then we're going to see which of the predictions is the most common, and that's going to be our voting method. We're going to use plurality. Now, the other way is that we're going to average them out. So if I have a regression problem, I have an observation that I need to make a prediction on, then my 500 different trees go and give me an individual value. Now, these are each individually a decision tree. I'm going to take all of them up. I'm going to average them out and see what I get. There are modifications to these two techniques, but these two are by far the most common. Random forests are able to capture very complicated patterns in our data, and also they're less prone to overfitting than individual decision trees. Now, why would we use random forests? Well, honestly, just from my experience, they produce highly accurate models. They can handle large data sets and high dimensionality, And they can handle thousands of input variables without having to do a whole bunch of like filtering of the variables. I don't have to put a whole lot of heavy lifting into this. Also, we get an estimate of variable importance in my classification and my regression problems, and they can be used for regression and classification tasks. Now, there are other uses in, so if I'm like in R, we can have like a survival random forest, but in scikit-learn, it's regression and classification. So that's all I'm going to talk about here. All right, so for a decision tree, and this is a copy and paste from a previous video, a decision tree splits the data into subsets using a series of decisions. Each decision is based on the value of the input variable. This results in a tree-like model of decisions. A decision tree is a flowchart-like tree structure in which each internal node represents a test on an attribute, a predictor variable. And so is the predictor variable value above or below a cutoff? Is it in this subset or in that subset? Each branch represents the outcome of the test, and each leaf node represents the class label that will be either the level for classification or the average of all observations in the leaf. All right, now under the hood, random forests are random in two aspects, rows and columns on the training data frame. All right, so here, and this is using scikit-learn's version of it, rows are bootstrapped. And so in this situation, let's say I have 1,000 training observations. I'm going to sample with replacement 1,000 observations. So some of those are going to get sampled multiple times and some are going to get left out. And so this is where that random aspect comes from. Other implementations of random forest will actually just do a random subset. And if it's important to you, to your project, just check your help documentation. Now here, columns are going to be sampled without replacement. And the number of columns will depend on the parameters you put in. Could be like half, could be the square root of the number of predictor variables you have. Some value could be as low as 3, whatever it is that you set up to be. And so now different implementations of random forest are going to implement this randomness different. So it's just something worth it. If you're going to be doing this a lot in any lane, just go read your help documentation. Make sure you know what's up on this one. All right, now for bootstrapping. So in scikit-learn, random forest uses bootstrapping. So this is resampling our observations with replacements. And so for each individual tree, a new bootstrap sample is generated. If I'm going to generate 5,000 trees, or excuse me, if I generate 500 decision trees in my forest, I'm going to be taking 500 bootstrap samples of my observations. Now, also, we're going to have feature randomness. In traditional decision trees, at each split, the best split among all variables is chosen. All right, so that's regular decision trees. In regular decision trees, we consider every single possible variable at every single potential split. However, in random forest, at each split, a random subset of features is chosen, and the best split among those features is determined. Now, there's a couple different ways that this can be implemented also. We could have the subset predictor variables fixed for a tree, or we could randomly select at each split. There are different implementations that do it different ways. And so by doing this randomness, we get more diversity in our model, and we make sure that we don't have correlation among our individual trees. And so how is a random forest built? We're going to draw a bootstrap sample equal to the number of observations that we have for training. We're going to grow a decision tree from the bootstrap sample. At each node, we're going to randomly pick a subset of predictor variables. We're going to pick the best possible split we can using one predictor variable. And then we're going to split the data in the node by the cutoff. And then we're going to repeat this for all of our trees over and over and over. And then when I'm all done, when I make a prediction, we're going to aggregate the results. If I'm doing a classification problem, each observation is going to get one classification from each individual tree. So that one classification observation has 500 different classifications from 500 different trees. They may be different. They may be the same. What we're going to do, we're going to just see by voting which one's most common. That is our final classification. Also, the distribution of the classifications give us like an empirical probability or a modeled probability on what the classes will be. Now, if I'm doing a regression problem, what we're going to be doing is that I'm just going to take the average of what the trees give me for the one observation. All right, now there's a bunch of estimators or a bunch of parameters that we will use. So in estimators is the number of trees I'm going to use. Criterion is going to be the function for measuring quality at the split when I'm doing classification, or it could be the measure of quality for split and regression. Notice I have, so these are both both parameters for classification and regression in scikit-learn, but you'll notice they have different possible values. So I put it on two different rows. Now the max depth, typically, max depth, typically we don't mess with this one. We just let it go. We let it go as deep as it wants to go. And so something that's interesting about random forest is that you can think of random forest is going too deep, and stochastic gradient boosting is going too shallow. And then individual decision trees are just right. So it's kind of like a Goldilocks problem. So when I do stochastic gradient boosting, my individual trees aren't deep enough, but because I'm modifying based off of previous results, we get a good overall model. With random forest, I'm going too deep on individual trees, but it ends up averaging out when I consider the entire tree. And so, it's an interesting aspect of the models. Typically, we don't restrict max depth, though we can. It will actually speed up the modeling potentially if we reduce max depth. Now, minimum number of samples to split default is 2. Of course, minimum needed to split some data. A minimum number of observations and a leaf default is 1. So what this is saying here, these three are saying let it go as deep as it wants by default. We don't have to put any restrictions on this. Now, I have had problems with overfitting with random forest, and the minimum sample leaf of 4 has always solved that problem for me. And so if someone's ever worried about going too deep, put minimum sample leaf down to 4, and that, in my experience, that's good enough. And now the rest of these, like max features, we have square roots or log2 are the default ones that we go with. And we can go through this. Now bootstrap and OOB score. Bootstrap here, we're saying whether we want to be doing bootstrap or do I want to just take data straight instead of having like that resampling aspect. Now out of bag score, what this will do is that this is going to take the observations that are not included in the bootstrap and use them as a holdout set. So this is a really good I'll talk about this more in a moment. So the out of bag score, I'm going to do my bootstrap. I have 1,000 observations. I resample my data with 1,000 observations with replacement. Okay, so some observations are going to be in my bootstrap sample multiple times. Well, it's going to work out. That means that some of them are going to some observations are going to get left out. What I'm going to do is I'm going to take the ones that get left out, use those as a holdout set. And with the holdout set, I can evaluate what's going on to evaluate each individual tree in my ensemble. All right, so the most important parameters for us are max depth, minimum sample split, and minimum sample leaf. These are the ones that we can use to make sure that, like if I build my model, I check my train validation and test statistics, and it looks like I've got overfitting. These three can solve that for us. And so I can modify these. I can decrease max depth, increase minimum sample split, or increase minimum sample leaf, and be able to correct this pretty easily. My experience is that just a regular old 4 for minimum samples leaf is enough to prevent problems with overfitting. All right, now when it comes to the situation where I have fewer observations than desired. All right, random forest is like the model that keeps on giving. So let's say that I've got enough data, I feel like, to build a model, but I don't have enough to do a proper partition. So I don't have enough to do a train test split. Well, what I can do instead is I can use the out of bag score as my holdout data for this purpose. Now, when it does this, this is going to be going off of individual trees as the for the holdout set. Because remember, when I did that bootstrap, each individual tree has a different bootstrap sample. And so this is just something to be mindful of. Now, in my experience and I haven't seen this written down, I haven't, heard anybody talk about this on blog posts or anything like that, but my experience is that out of bag scores tend to be optimistic. Not as optimistic as training statistics, but still a little bit optimistic compared to validation and test. So just take that, keep that in the back of your mind. If you're in the position that I need to build a model, I don't have enough to do a train test split, and I need to, I can't spare anything, and I'm going to use my out of bag as my measurement of model quality. Just remember that it's going to tend to be potentially a little bit on the optimistic side. All right, so now some things that I can do to improve computation time is that I can, so I think I'll have to fix this before class. So if computation time is an issue, I can decrease max depth so that trees don't go as deep. I can reduce the number of trees that I use. I can do anything that prevents trees from going deeper, so it will increase sample splits. I can increase minimum sample leaf, and also I can decrease the number of predictor variables involved in each individual tree. And this usually can address any problems with computation time. Now, for data preparation, once again, decision trees are the way to go if you want to be lazy on your data prep. Tree models need less data prep compared to others. So monotone transformations such as square roots, or so assuming I have like positive data, if I do a square root or a square or anything like that, logarithm, anything that does not change the order. So like if I have positive and negative data and I square it, then -1 was less than 0, but when it's squared, it becomes positive, it's greater than 0. That is a non-monotonic transformation because -1 was less than 0 before the transformation gets transformed. The point is 1, which is greater. It switched the order. Any transformation that does not change the order of our data will not improve or degrade a decision tree model. Also, centering scaling will not change the performance of the decision tree. Coding ordinal predictors as numbers will not change the performance of the decision tree. Now, some implementations of decision trees can only use categorical predictors in a binary format. So like scikit-learn can only use numeric values, unfortunately. I can't keep raw values in. And so that's something I might have, depending on the implementation, I might have to deal with that. Now, there are implementations such as SAS Enterprise Miner that it'll take categorical data and it will find the best subsets for the split on there. Now, if there are a lot of levels for a categorical predictor variable, think of like state, has a lot of different levels, then this can take a long time to compute. So be ready for that. All right, so when we're doing, so if I have numeric or ordinal, like integer ratio data, and I have k distinct levels, k minus 1 possible splits are possible. And so if I need to speed up computations, again, another thing I can consider is just rounding off values. That way the algorithm has to try fewer distinct cuts. Now for categorical predictors, we're going to have 2 to the k minus 2 as the number of possible partitions to apply. Why is that? Well, because how many subsets does a set have? Well, 2 to the k, but we know we're not going to use the empty set. We know we're not going to use the full set as for a split. So that's where that -2 comes from. Categorical predictors that are not in the dummy coded version with a lot of levels can cause random forest to take a long time. Oh, I talked about this previously. I should have removed it from above. By reducing the number of trees, we can improve our computation time. If we reduce the max depth, the trees don't go as deep, takes less time to fit individual trees. Reducing all of these are basically just saying, hey, don't make the tree, make the trees go less deep to speed things up. Also, we can reduce the number of predictor variables in each, at each split. And so, we can, we can also require that the trees don't go as deep by increasing the minimum impurity decrease. So what this is saying here is that I have a higher criteria for having a split in my data. We can parallelize our work, and we also do a warm start if we want. We can also reduce the size of the training data by reducing max samples or just reducing the training data. We can also skip pruning. So pruning, we fit the tree, then we go back and we trim the tree afterwards. And also, if I need to speed things up, I can skip doing the out of bag score. By default, out of bag score is equal to false. All right, so the out of bag is a generalization estimate for us. My experience is that it's a little bit optimistic, but not as optimistic as training. This is a good choice if I'm desperate for data and I don't have enough to do a train test split. Now, by default in Scikit-learn, the out of bag score is actually R squared. So the predict value and the true value the correlation between the two is the out of bag score. So let's go ahead and run through an example. So here I'm going to be doing a regression problem on the Box-Cox transformed version of house prices. And I'm just going to run through a bunch of different parameter values. So I'm going to modify max depth, minimum sample leaf, and minimum sample split. These are the most important of them. And so something that I do, I always like to find some number that's really important to my organization, and I put in the number there for the random state. That way, when someone sees my code, they recognize a number that's really important. So like if 1810 was important to your company, because that's when it was founded, I would put 1810 right there. All right, so now let's go ahead and fit all of our models. So here, this is a list of regression models, but I have not fitted them yet. And you notice I'm using list comprehension to get through the list or get through the for loop. Now I'm using list comprehension for the for loop also to go through and fit the individual models. And now I have a data frame of all of these predictions. So now what I'm going to do, I want to check and see which of these models does the best job. And here I'm going to choose to use mean squared error. Mean squared error is most of the time the default loss function for a regression problem. It's a good choice if I want to avoid big errors. My experience in real life modeling is that really overall accuracy is not as important as avoiding big mistakes. And mean squared error does a good job avoiding big mistakes overall. Because if I have an error that's greater than 1, when I square it, it gets bigger. So anything greater than 1 to square, the result is bigger than what it was before. Anything less than 1 in magnitude that's squared becomes less than it was before. So if I have a big error in my model, when I square it, it gets bigger. And so this helps identify models that are not going to do as good of a job avoiding the big mistakes. Now the rest of this is just basically slugging through to get things in the right format. And I end up getting, here's the column of models. Here's test statistic, validation statistic, train, and out of bag score. So train, validation, and test are going to be the mean squared error. While the out of bag score, this is actually R squared between the observed and the predicted values. And this is using the out of bag observations for this. And so, we can scroll through and just see what's going on. Remember to always compare your test and validation to your training statistic. Notice that the training statistic is better than test and validation. That's how it typically is. All right, so if the gap is large, then I'm worried that I have overfitting. Now here, there is a difference in magnitude, honestly, but it's small enough that I feel like this is okay. Every model overfits. Honestly, every model overfits on its training data. This is no exception, but here, I'm okay with what's going on. Now, for feature importance, how feature importance is computed in scikit-learn by default is to look at how much of an improvement on the impurity did the feature provide in the model overall. And so I find that this is a really good overall way to judge how important a predictor variable is, but there's some drawbacks to this. First and foremost, we can have misleading for high cardinality features. So if we have many unique values, we can have misleading values for feature importance. Also, something that can happen compared to generalized linear models, logistic regression, multiple linear regression, things like that. If I have a situation or I have a predictor variable that's very rare, but has a huge impact on what's going on. Imagine we're talking about bankruptcy. Bankruptcy is rare, but when it happens, like finances are just, all right. So if I'm working on, let's say, a collections model on who I should target for collections and who I should just write off, bankruptcy is going to be relatively rare, even in the collections lanes. It's a rare event, but it has a huge impact. And since it doesn't come up very often, it's going to end up that tree models aren't going to give it as much importance as it should compared to, like, let's say, logistic regression. Logistic regression would give it a bankruptcy, a huge coefficient, but it's very rare. It doesn't come up that often. So this is just something to think about when you look at your feature importance. Every different model structure is going to do feature importance slightly different. Make sure you understand which one you're looking at any given time. And so now, something that happens when we do feature importance in scikit-learn is that everything is rescaled so that it adds up to 1. And so we can see that overall quality of the home accounted for about 42% of all the feature importance altogether. Then ground living area is a little bit over 20%. Then first floor is about 8%. And we can keep looking through this, and we can see that typically, usually when you have a good model, you're going to see a Pareto distribution that 20% of your features account for 80% of your importance. Be ready for that. It's okay. So now, one thing that I can do is that if I wanted a simpler model, I know that I could get rid of this predictor variable, and I really would not be losing much. And as I go through, I could get rid of a predictor variable, refit the model, reassess feature importance, get rid of low importance predictor variable, repeat over and over and over. Now, something that's going to happen, if I have two important predictor variables that are highly, highly correlated with each other, imagine that they're, for all practical purposes, the same columns, and I made a mistake, I didn't do proper feature selection, something that's going to end up happening is that they're going to kind of eat into each other's importance. Let's say that one of them should have had like a 0.2 importance if I had either one alone, but together I put them in, they'll have like a 0.1 importance. And so collinear predictor variables are going to eat into each other's importance. So it's important to go through and make sure I do my proper feature selection before I put a model into production. All right. I love random forests. Random forests are my favorite model structure. These are a good choice when I need a model fast and I need to take data, get an answer, get something going very quickly without having to go through the full proper process. If I need to give answers right away, maybe during a meeting, I've used random forest multiple times that my stakeholders have a question in the first 15 minutes of an hour-long meeting. By the end of the meeting, I use random forest, boom, I've got an answer to the question they had previously. And let me tell you, that makes you look good. That makes you look competent when you're able to deliver on questions that they had and you produced it in real time. This will help you professionally a lot because they know that you can deliver. Also, this prevents you from having to go back into more and more meetings, having to schedule a meeting and get everybody involved, find some time that fits everybody's schedule, then get everybody to sit down, like restart the entire meeting, talk about it. I hate that experience. I'd rather spit out an answer immediately. All right. Well, this is all I've got for you. Life is short. Do math.